Okay, I'm going to go ahead and start recording. Okay, the hydrates lab, go ahead.
Um, it's asking like with the percent error, with finding that out, I had a hard time.
Many ways of doing it. Okay, so for the hydrates lab, let me share my screen with you so you can see what I'm writing, okay? Now, for the hydrates, there are basically three hydrates. One of them really isn't a hydrate. So there's this, there's this, and there's this. Now, the easiest way to calculate a percent error is to look at something in here and compare it, what you get to what you should have got. So your formula for whatever you got should look something like this. Calcium sulfate, maybe it's like 3.2 H2O. Are you with me here?
Yeah.
Because you're going to calculate moles of H2O, and this is based on mass lost, right?
Right.
And you're going to calculate moles of calcium sulfate, and that's based on mass remaining. And then what you're going to do is you're going to put this over that, divide y into x, and you'll get that number. Okay?
Right.
So now if you get this as your formula, you clearly do not have that guy. Does that make sense?
Yeah.
So what makes the most sense is that you have that guy. So here, what is the number here compared to the number here? And the answer is it's 1. So you have the feeling that just because that's a 1 and that's a 1, that doesn't mean that this is perfect. The number here is a 2, the number here is a 3. Percent error is always going to be what you got minus the shoulda over the shoulda times 100%. So do you understand what I mean by when I say shoulda?
Is that like the accepted?
Yeah. So you should have got a 2, but you got a 3.2. So it would look like this. And this would end up being 1.2 over 2 times 100%, which would be 0.6 times 100%, which would be a 60% error. Okay? And, you know, some people think, well, oh my goodness, I got a 60% error. I'm going to fail the lab. And the answer is no, you're not. You need to tell people why you got that error. Because if you don't tell people a good reason for why you got that error, then you get to fail the lab. So what might be a reason why you get a 60% error? Well, let's talk about this number. It's positive, not negative. So positive means your value is too large. Now, when we take a look at this value and we calculate it here, it either means one of two things. This one was too small, or this one was too large. Now, what's the likelihood that you have too little calcium sulfate? And the answer is no, you can't, because you can't cook it away. Okay? But on the other hand, what if there were impurities in your material and you did cook away some stuff that you didn't know about? That could explain it. On the other hand, why might you have too much H2O? Well, it may be that some hydrates actually suck water out of the air. That is a possibility. And so being this being Humboldt County and being rather humid, maybe the compound absorbed water from the air, and that's why there was more H2O in there than we expected to happen. Does that make sense?
Yeah. No, that makes sense. Thank you.
So it's not, you know, I'm not looking for you to get a small percent error, I'm expecting you to analyze your results. And if your results say you get a 60% error, then fine, you got a 60% error. Let's try and figure out why. Okay? All right, good question. Anyone else with a question? I know the question burning in most of your minds, when is he going to get those exams graded? Not until next week. Most people ask, when will we get them back? And my answer is after I grade them. All right, so you guys don't have any questions. Have you noticed, so I'm going to do a different share screen now. Have you noticed some of the items that I've posted for the next module? Let's go over them real quick. So it doesn't matter what section you're in. The things I posted are identical. I'm going to close module 1 since we're pretty much done with that. Module 2 we're done with. Module 3 we're done with, except for the hydrates. And let's focus on module 4. So you can see that for module 4, I've actually posted a PowerPoint presentation. And you can download it. But this is a very good way to quickly go over the stuff in chapter 4. And why isn't it showing up here? Oh, it is showing up. So you can see that there are 9 sections in this chapter. And looks like, based on what I'm seeing here, it'd probably just be easier to download it and then look at it using PowerPoint. Okay, so I would go ahead and take the time to just kind of glance through these to get an idea of what's coming up in chapter 3. Or I should say the next module. This is chapter 3 of the 10th edition. So now I'm going to close this, if I can. I'm just going to go back to here. Boom. So apparently it takes a while for Canvas to recognize that I have closed module 1. So here, if we look at the chemical reactions video lectures, they look different than they have in the past. And I think they're better. So here, if we look to the right, can everyone see that there are 5 videos posted so far? And if you look at the titles of the different sections in that chapter, the titles of the video are matched to the titles of the section. So if you're having trouble with precipitation reactions, you can watch the precipitation video and not figure out which video you need to look at to see that particular topic. Any questions about that? So you can see from my sharing here that you can see 5 lectures. It says 5 videos. I've only posted 5. 4 more will be posted. I hope to post those tonight, but I don't know if it's going to happen. Okay. So I'm going to go back here to the module. Actually, I'm just going to go back to the home page because the home page automatically takes you to the modules. You'll also notice that in the 4th module, I've posted the precipitation reactions. It's the new lab that you're supposed to be working on this week, along with another one I'll be posting tomorrow for this week. So here's the link to the lab notebook. And what I should really write here for the intro is I should start off with instead of background, I should start off with write this up in your lab notebook and include photos. That is the assignment for the lab notebook. But of course, you know, I do want to give you some background about what's happening. So you want to read through this. This is not necessarily stuff you want to put in your introduction. Like here, I have a little diagram that shows you if you have an ionic solid, a three-dimensional lattice of ions, and you can see that it's very well structured. When you add water, the ions separate from one another. And this little wavy thing at the top is supposed to be the top of my water. And I show you how to write that symbolically and so forth and so on. And I give you some hints about things that you might want to put in. You definitely want to put safety in. Here's your procedure. We're basically doing two different things, solubility and precipitation. I give you some hints on data. Calculations, you're supposed to think about whether or not there's supposed to be any calculations. Results also. And you should write a discussion. And you can see at the bottom I wrote, submit images also. Okay, so that's your lab notebook. Let me close this now. And I'm going to go back to the home page, because the home page always gets you to the modules. And the modules are here. And you can see what the due date is for the precipitation reaction lab notebook, right? September 29th, which is next Tuesday. So you've got 6 days to work on this. And then here's the precipitation lab assignment. So here's the link. And here's the lab assignment. Okay, so I'm going to close that. So that's what's been added. I'm going to go back to the home page. And for module 4, the things I'll be adding today are things like the discussion where you're supposed to participate. I'm going to be adding, hopefully today, the module 4 homework assignment. And we'll also add, what else am I going to add? The rest of the video lectures will go into the video lectures. There will be another link here that'll say chemical reactions Q&A videos. So today's video will go into that link. And what else am I going to post? So what I'm trying to do is make each module look pretty much like the previous module. I don't like having a whole lot of links in each module, but I have to put separate links down for different things. If anything, I should probably edit this and call it something else. What should we call this one? Rather than chapter 3, let's call it chemical reactions PowerPoint. How does that sound? I do like naming these things so that you have a better idea of what is behind it, if that makes any sense. Okay, so what you can expect later is tomorrow, another lab. I should give you some fair warning. For the next lab, you're going to have to buy some things like sodium bicarbonate, baking soda, which is baking soda, vinegar, and red cabbage. Let's see. I'll be posting hopefully the rest of the videos. I might stay up tonight and try and get that all done so it's out of my hair. I'll post today's lecture. All right, so that being said, does anyone have any questions that they'd like to ask about anything? Okay, so since there aren't any questions, I have a few prepared for us to look at. So the very first section of this chapter talks about writing chemical reactions. And so as you will be able to see in a moment, but you can't see right now because I've forgotten to share, you can see this question here. This is from the book. And I'm going to give you a moment to read it. Okay, so when they say write an equation, what do they mean by equation? They mean chemical reaction. Okay, so from the following description, reactants are gaseous ammonia and O2. So when we are talking about reactants, this is what we begin with. And almost always we put that on the left. So there's ammonia. When they say gaseous, they mean we should write the state behind the formula in parentheses. Now this gaseous applies not only to ammonia, but to O2. So for the next next substance, we're going to put a plus sign, put its formula down, and then that. Now, if all of this seems really rudimentary to you, that's great. It's supposed to, because you've taken a chemistry class before. Okay, now when they say products, what you want to do is you want to delineate between reactants and products with this arrow. And the arrow points away from the reactants and towards the products. So we have gaseous NO2 and liquid H2O. And then they tell us the stoichiometric coefficients are 4, 7, 4, and 6 respectively. What does that mean? Well, the stoichiometric coefficient goes in front of the substance. So we would have 4 here, 7 here. You'll notice I leave a respectable amount of space there because if I don't, it's going to look like 70. We're going to put a 4 here and a 6 here. And you might wonder, well, why those coefficients? And the reason is because this chemical reaction, which is balanced, shows that the atoms on the left are the same as the atoms on the right, and the numbers of those different atoms on the left equal the same numbers on the right. In fact, if we make a list, nitrogen, hydrogen, and oxygen, and count the atoms on the left, we have 4 times 1, 4 nitrogen atoms. So the way to count nitrogen atoms when we include the coefficient is to multiply the coefficient times the subscript. So this 4 NH4 really NH3, I'm sorry, means this. And you know chemists are more proficient with their time than writing out NH3 4 times. So you put a 4 there. How many hydrogens are there? Well, 4 times 3, there's 12. Oxygens, 7 times 2, 14. Now, here's something you don't want to do. You see how we have a nitrogen here, an oxygen here, and a hydrogen there? We don't want to write down another oxygen. This is something we don't want to do, but I'm going to do it anyways. 4 times N, 4 times 1, 4 nitrogens, but oops, what about here? Well, lucky for me, there's no nitrogens. How many oxygens here? 8. So I'm not going to put 8 down here because I see there's more oxygens over here. So we've got 8 plus 6 for 14. How many hydrogens here? None. How many here? 12. And can you see that these lists match? They do, but it's not very easy to tell. It would be a lot easier if I wrote this list this way. So I could match them in the same order. So this is a common technique for balancing really rough reactions. You make a list of each one, and you make sure that you end up with the same numbers of each different element on each side of the equation. So what is the interpretation of this? Well, in this particular case, each one of these is a molecule. And the reason I say it's a molecule instead of an ionic compound is because they're made out of non-metal elements. So each of these is a molecule. So we would say 4 molecules of NH3 gas react with 7 molecules of O2 gas to produce. Now here, we can use a number of different words. We can put to form, to make. I like the word produce because what do you produce in a chemical reaction? You produce products. So to produce 4 molecules of NO2 and 6 molecules of H2O. Now let's do a little practice for that last exam. If we did not know that this was named ammonia, which it is, what would its name be? So you don't need to answer outright or anything. Just think about what its name would be using that binary molecular method of naming. When you have the name in your mind, go ahead and give me a thumbs up. Are you there, on? Well, I'm going to go ahead and you don't know the name or you're not there. I'm kidding. If you put a
I'm not
thumbs
sure
down,
how so.
so this would be called nitrogen trihydride. Remember how we name those things? You name the first element like the element, the second element, you name an ide. How would we name this guy? Well, this one does not have a binary name. It's just called oxygen. So now I want you to think about how to name that guy and give me a thumbs up when you think you have it. So nitrogen dioxide. And how about this last one? How would you name that one? Not water, but naming it using this binary method. When you got it, give me the thumbs up. Okay, so dihydrogen. Now, why is this called hydrogen here, but over here it's called hydride? Anyone want to vocalize the answer?
Oh, because the hydrogen is in the first element.
Right.
And
When
the
it's the
hydride is
first
in-
element, it's the name of the element. And you use a prefix if you have to. If it's the second element, it becomes ide. So dihydrogen monoxide. Monoxide is also acceptable. Although when people see this, they often get confused and they go, is that monoxide? And no, it's monoxide or monoxide. Are you with me? Okay, good. Let's do another problem. So you can see these problems are pretty easy so far. And I'm going to throw in the opportunity to backtrack and look at stuff we've done before and think about things we've done before because you will need those things in the future. So I'm going to give you a moment to read this. Okay, so before we actually do this problem, what is really funny about one of these formulas? How does that formula look for aluminum? Is that okay? The answer is it is. How about Br? Should there be a 2 after it? Absolutely. What are the elements where if they're pure, you should have a 2 after the element? Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. Hung, coal, brif. Those are the ones that should have a 2 after it. So that's bromine should have a 2, but can you see that there is no aluminum here? That's why there's no 2 after aluminum. How about this formula? How does that look? To me, it looks weird because I think it should be this. Because ionic compounds, you simplify the formula. And yet it's written this way. So what in the world does that mean if the formula is written that way instead of this way, the simplest form? Is this something new I need to learn? And the answer is no. It turns out that this is actually a molecule. And sometimes metals can make molecular bonds with nonmetals. So the formula for this is Al2Br2 because that's how many aluminums and that's how many bromines are in one molecule. So that's why this has this formula. A little bit weird. So here I'm going to write 1, excuse me, I'm going to cross that out because that's wrong. If we look at just the coefficients, we're talking about 2 atoms of aluminum react with 3 molecules of Br2 to make 1 molecule of Al2Br6. Now, a little more digression. I want you to think about the name of this compound. And when you have it, give me a thumbs up. Remember, it's not ionic, so we name it like a molecular compound. How do we name molecular compounds? You name the first element first, aluminum. Do we use a prefix? Yes, if there's more than one. Well, there's 2. Dialuminum. And then we name the second element like an ide. And we always use a prefix. So what's the prefix for 6? Hexa. Dialuminum hexabromide. Okay, so this is what's happening in this reaction. And we can also write it this way. 2 atoms of aluminum equal 3 molecules of Br2, and that equals 1 molecule. Let me put the number 1 here, because here I have numbers and here I wrote out a 1. So now we're kind of set. When I see these as being equals, we can think of this as being possibly conversion factors. So if we use 6.0 times 10 to the 23 molecules of Br2, how many atoms of aluminum? Whoops. So to do this problem, what would be really nice is if we could do this. And multiply by something that has molecules of Br2 in the bottom, and it has atoms of aluminum in the top. So do we have that anywhere? And it turns out we have it right here. So what number belongs with molecules? 3. What number belongs with atoms? 2. And here is the work to show how we achieve the answer, which will be atoms of aluminum. And this one we can do in our head, right? 3 goes into 6.0 2.0 times. 2.0 times 2 is 4.0. So there's our answer. And that's the kind of work you would expect to see for something like this. Any questions about this one, people? Please raise your hand. If you're good on this explanation, give me a thumbs up. How you doing, Harry? I haven't heard from you for a while. I have the feeling that you're Zooming with another class while you're Zooming this one. Are you cheating on me, Harry?
I would never.
This is probably the first time you've been accused of cheating on someone from a Zoom session, hasn't it? This is a real question, folks. Have any of you ever Zoomed 2 classes at the same time? I'm kind of curious.
No, I haven't. They've always been separate times.
Okay. Is it even possible?
I think, yeah. Like this class basically didn't talk that much, so.
Yeah, it seems like you should be able to Zoom as many classes at a time as you want. But that could be a little tricky because you never know what's going to happen. Okay, I'm going to give you a moment to read this one. All right. So to do this one, we really need to have a chemical reaction. A sample of magnesium. So we're going to write magnesium. Because it's a metal, we know it's a solid at room temp. And because it's not a Hänkelbrief, there's going to be no subscript behind it. It's 1. Now, actually, I put that in there because I know what it reacts with, but we should really read the question carefully. Burns in air. Okay, so that probably means it reacts with something in air. To form, which is like produce, solid MgO. So if we have to ask ourselves the question, what does this have to react with to make MgO? It becomes very simple. In balanced reactions, the types of elements on the left have to be the same type of elements on the right. And here, since we have an oxygen on the right, we better have oxygen on the left. So if we put this in here, that would help. Now, we need to complete this. This is not a metal like magnesium. It is an element that belongs to the Hänkelbriefs, right? So you have to put a 2 here. And then we also have to think about what is the state of oxygen in air. It's a gas. So here's the chemical reaction. I think I wrote the problem down wrong. I think this is supposed to be 0.2. Okay. All right, so we have 0.20 mole, and you get 0.20 mole of product. Question is, how many moles of oxygen? This almost looks like CO2, so I'm going to extend the parentheses so you can see it's O2, are required for the complete reaction. Well, this says 1 atom of magnesium is equal to 1 molecule of O2, which is equal to 1 formula of MgO. We can't call that a molecule because it's ionic, it has a metal and a nonmetal. But these stoichiometric coefficients are just ratios. And here, we do need to balance the reaction. And to balance the reaction, we would put a 2 here and a 2 here. So that means this becomes 2 atoms of magnesium react with 1 molecule of O2 to form 2 formulas of MgO. These stoichiometric coefficients are ratios. So we could say 2 moles of magnesium react with 1 mole of oxygen, and that equals 2 mole of MgO. This mole thing is kind of nice because then you don't need to write things out like atom, molecule, or formula. So we can use this to actually do this problem. So if we start off with 0.20 mole of magnesium, we want to multiply by something that has mole of magnesium on the bottom and mole of O2 on the top. So where do we get that? From right here. It's 1 mole of O2 and 2 moles of magnesium. So we need 0.10 mole of O2 to complete the reaction. If you're okay with all of that, go ahead and give me a thumbs up. Okay, we'll move on. So, I don't know if you've watched my lectures, but I tell you that when you are balancing reactions, we follow the law of the conservation of matter, which basically says you cannot create matter or destroy matter. But in a chemical reaction, it means that whatever you start with, you have to end up with the same atoms. Maybe not in the same arrangement, but the same atoms. And to do that, we are allowed to change coefficients. We are not allowed to change the reaction. And so here, just a very quick balancing do and don't. Do change coefficients. Do not change formulas, because that means you're changing the reaction. So for instance, this is a reaction that does occur. Hydrogen reacts with oxygen to give you H2O. So this is a real reaction. So this is a don't. Do you see how we have 2 hydrogens on the left and 2 on the right? This is a don't. Do not change the formula of anything. So this is a do. If I put a 2 here, I'll end up having 2 oxygens. and I have 2 oxygens over here. But if I put a 2 here, instead of having 2 hydrogens and 2, I now have 2 and 4. So I'll put a 2 there. So this is the do, and this is the don't. Are we clear on the do and the don'ts for balancing? So let's take a look at this problem here. What I do with the problem. Here it is. Write balanced chemical equations for the following reactions. So I'll go through the first one with you, and then I'm going to let you do the second one and the third one, and we'll check our answers. So the production of ammonia. So that means that ammonia is a product. By combining N2 and H2. Now, when you write these out, you would like to leave space in front of the formula of the substance so that you can put a number there if you need to. So when we check here, you can see that we have 2 nitrogens and 1 nitrogen. So how do we get 2 nitrogens on the right? Put a 2 in front of there. So we've essentially gone from NH3 to NH3 plus NH3. We're just adding another formula there. And a common question people ask is, well, where did you get that other one from? And the answer is, we didn't get it from anywhere. We're just trying to get the right recipe. We're just trying to get the right recipe. Okay, so here's the right recipe. If we start with 2 nitrogens, we need to end up with 2 nitrogens. But we're ending up with 6 hydrogens, and we only start with 2. How do we start with 6? We put a 3 in front. And so now this is a balanced reaction. And this balanced reaction says 1 molecule of N2 reacts with 3 molecules of H2 to give you 2 molecules of ammonia, or 1 mole of N2 reacts with 3 mole of H2 to give us 2 mole of NH3. Okay, so you give this one a try and give me a thumbs up when you're done. So production of methanol, is this going to be a product or a reactant? Now, it happens to be a liquid. I don't think the problem tells you that, but it's a liquid. It's a product. And we know it's a product because it says production of, so it's produced. Okay, let's try to balance it. Now, I'm actually not going to do the hydrogen first. I'm going to do it last. And the reason is because if I had to change the coefficient in front of this, it doesn't change anything else. If I change the coefficient in front of here, it changes both carbon and oxygen, and I need to take that into account. So I'm going to skip this guy for now and go straight to carbon. Carbon, there's 1 here. Carbon, there's 1 here. That's good. Oxygen 1 here. Oxygen 1 here. That's good. So now I'm going to do my hydrogen, and there's 4 here. So if I change the number here to a 2, I will have 4 hydrogens, and I don't need to go back and check my carbon and my oxygen because I did not change the coefficient there. So this is balanced. Any questions? All right, so try this one now. The production of sulfuric acid by combining sulfur, oxygen, and water. Now, that is the formula for sulfuric acid. You need to figure out what the formulas for these are. So the H2SO4 is going to go over here. Now sulfur, is that a element that deserves a 2 behind it? What do you think? If you think it deserves a 2, put yes. If you think it doesn't deserve a 2, put no. No is correct. It's not a Hänkelbrief. What about oxygen? Does that deserve a 2? If you think so, put yes. And the answer is yes. Han, coal, brief. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. Those are the ones that get a 2. What's the other way of remembering this list instead of Hänkelbrief? Anyone know? Have no fear of ice cold beer. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine. So either one will do. Or if you don't like either of these two, invent your own so that you can memorize that and not have to put it on a 3x5 note card. Okay, now what about the formula for water? What are we going to write? H2O. Okay, so let's set about balancing it. 1 sulfur, 1 sulfur. 2 oxygens, 4 oxygens. So I'm tempted to put a 2 here, but if I put a 2 here, I'll end up having 5 oxygens, and that's not cool. Okay, so I'm going to skip the oxygen and go to hydrogen. 2 here, and now I'm in a bit of a quandary. I need 4 oxygens, and I have 3 over here. How can I end up getting 4 oxygens total? Because these all come in 2s. And I'm going to show you a little trick. So we're going to have 2 oxygens here plus 1 oxygen here. And from this amount, we need to end up getting 4. I don't want to change this coefficient. I want to leave it as a 1 because I want 2 hydrogens. So we're going to leave that as a 1. So now we have kind of a formula here. And the formula is whatever this coefficient is, I'm going to call it x. X times 2 plus 1 has to equal 4. If I get the right x, I will end up with 4 oxygens. So if I make that 3 halves, I should have 4 oxygens. So let's check. 1 sulfur, 1 sulfur. 3 halves times 2 is 3, right? 3 plus 1 is 4. 4 oxygens, 4 oxygens. 2 hydrogens, 2 hydrogens. Now this is not a correctly balanced reaction because you can't have a half of an oxygen. So how do we balance this correctly? Remember, these are just ratios. So we can double each number. And it should be balanced. Let's check. 2 sulfurs, 2 sulfurs, 6 oxygens here, plus 2 more here for 8. 2 times 4, 8 oxygens here. 2 times 2 for 4 hydrogens, and 2 times 2 for 4 hydrogens. It's balanced. Any questions on this one? Because this one is challenging. The little halvesy thing. You're going to find that when you watch the lectures for balancing oxidation reactions of hydrocarbons, sometimes you use the halvesies. Okay, this is the last thing that I have prepared for you. So we're going to balance this and go from there. But before we balance it, let's name these things. So what do you call this element here? Chromium. What do you call this element? Chlorine. If you think this is molecular, put yes. If you don't think it's molecular, put no. So the question is this molecular? You guys are absolutely correct. It's not molecular. So that means it needs an ionic name. So what are the ions here? Well, you've got a chromium ion with a positive charge of some sort. I'm going to put question mark there because we don't know whether it's a 1, a 2, a 3, or a 4. And you've got 3 chlorides. We know there's 3 of them because of the subscript. And we know that chlorine ions have a charge of -1. So based on this, the chromium has to be a +3. If this is in group 1A, 2A, or 3A, we don't need to tell people the charge. But when we look at chromium, it's not in 1A, it's not in 2A, and it's not in 3A. Chromium is over here somewhere. So we need to tell people the charge. So this is called chromium 3 chloride. Okay, now let's balance it. Now we could do the halvesies things. I could put 3 halves here and that would be balanced, and then I could double everything. Another way to do this though is to take a look at this. I've got 2 chlorines here and 3 here. I could just multiply those 2 together. 2 times 3 is 6, and say, okay, I want 6 chlorines. To get 6, I need to put a 3 here, and I need to put a 2 there. And you'll notice I ignored chromium at the get-go because it's a substance with a single element. I can change the coefficient in front of that without messing anything else up. So now when I change this, it does mess up the chromiums, but it matches the chlorines, but there's the easy fix. 2 there. So you want to balance substances that are pure elements last. So here, I'm going to balance the carbon last. So silicon, I could do the silicon last. So here I've got 2 oxygens. Now I've got 2 oxygens, but now I need 2 carbons. So I put 2 there. Here I have 1 silicon, we're done. What is the name of this compound? And this is something you just need to learn over time, is that when you name compounds that have metalloids in them, you usually name them like molecular compounds because they usually make molecular bonds. This is just called carbon. This is silicon. And this is carbon monoxide. Okay. Try and balance that one. When you're done, give me a thumbs up. Okay, you're all done. I'm going to put a 3 here for the irons. I'm going to put a 2 here, so I have, oops, excuse me. I'm going to put a 4 here, so I have 4 oxygens here and 4 here. And I need 8 of these, so I'm going to put a 4 there. Okay, good. Now, name each one of these using binary molecular names or ionic names or element names as appropriate. When you're done, give me a thumbs up. All right, Harry, are you extremely confident in your answers? If you are, give me a clap. You can find the clap under more. Okay, well, let's go ahead and name these. Let's do the easier ones first, the elements. This one's called iron. It's spelled iron, but you say it iron. This one here is called hydrogen. What do we call this one? Dihydrogen monoxide. So where does the coefficient come into play when we're naming these things? And the answer is not one bit. When we name compounds, we don't care about the coefficient. So what is this guy? It's this, right? This has a total charge of -8. What does this have to have? A total charge of +8. Now, irons come in 2 flavors. +2 and +3. So how would we name this? And the answer is we don't know. Alls we do know is there has to be 2 of these in one of those. Okay? So honestly, we haven't covered how to name these, and in all of my chemistry classes, we haven't covered how to name these. So if your answer is, I don't know how to name that, ding, 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 you're correct. You don't know how to name it. I don't either. And that's okay. So any questions about this guy right here? That would be something that you would not be asked on an exam, how to name that. Okay, that's it for today. Do you have any lingering questions you'd like to ask? If so, please ask now. Okay, since you don't, go ahead and turn your mics on and say, see you guys Friday.
Bye, guys.
Hey guys.
All right, thanks for
You're
coming.
welcome.
I appreciate it.
Yep.
Bye-bye.